It gives me great pleasure to introduce today's CFA colloquium speaker, Dr. Erica Nelson. So Erica received her PhD from Yale University, working with Peter van Dockum. Then she did a postdoc at the MPE in Munich before taking a Hubble Fellowship here. And then she moved to Colorado, where she's now an assistant professor, is that right? Mm-hmm. Yeah, so she's on the faculty at the University of Colorado, soon to be promoted, I assume. So Erica is an expert on high redshift galaxies. So for her thesis, she did a lot of work on galaxies at redshifts 2 and 3, looking at their properties, in particular their sizes, and found some interesting compact objects that might be the cores of today's very large elliptical galaxies. But not being satisfied with redshifts 2 and 3, she's since moved on to even higher redshifts using the Webb telescope, which is what she's going to tell us about today.
Thanks, Lars. Is there, oh yeah, perfect. Yeah, could have some dark stuff to show. Hi everyone, it's so great to be back here. It's been a while. I left during the pandemic, which was an extremely sad thing, but it's great to be back at the CFA and to be here in Phillips with all of you guys. So today I want to start I'm going to talk mostly about new observations that we've done with James Webb and some new methods that we've developed in order to get more out of this incredible new telescope. But before I do that, I want to talk a little bit about the history pre-James Webb, what we knew about galaxies, what we knew about the universe. I'm not a history buff, so like if I mess something up, I apologize. A lot of you probably know this history better than I do. So just, shout at me if I say something wrong. Before we talk about distant galaxies, I wanted to start a little bit closer to home, well, my home in Boulder, Colorado. So Boulder, Colorado is where the primary mirror segments for the James Webb Space Telescope were built. It also happens to be the land of milk and honey. It is a beautiful, spectacular place. If you are a graduate student looking for an awesome place to do a postdoc, I can strongly recommend Boulder, Colorado. This is me on one of my favorite climbs, writing the analysis section to my first James Webb paper. Boulder, Colorado, where these mirror segments for the James Webb Space Telescope were built. So we have these 18 gold-plated beryllium hexagons that form the 21-foot tall golden mirror for the James Webb Space Telescope. They've been shipped all over the world, and they were assembled into the beautiful telescope that we see today at the Goddard Space Flight Center. This telescope has actually been in the works for longer than at least most of my undergrads. I'm not sure about anyone in this room per se, but like at least most of my undergrads, this telescope has been in the works longer than a lot of them have been alive. Work started on this thing in 1996, and so we, 2 to 3 decades, $10 billion, and we finally have this remarkable telescope. This is it getting shipped down the Pacific Ocean through the Panama Canal last year on the way to French Guiana, where it was launched into space last year on Christmas Day. So this is, can we have audio?
T-minus 30 seconds and counting.
That might have been starting it too early.
Standing by for terminal count.
30 seconds is a long time. Really thought I queued that up for like the 10 seconds. Oh, there we go. Okay.
7, 6, 5, 4, 3, 2, unité, top.
And we have engine start. And
Allumage
liftoff.
UAP, décollage.
Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
Yeah. The edge of time itself, you heard it here
Punching
first.
a hole through the clouds, 20 seconds into the flight, good pitch program reported.
So this launch, it didn't blow up in the launch pad. That was success number one. And then, you know, this is the last view. We're going to skip that. So that was really loud, and it was strange music. Did not know that. Okay, so what I was going to show you is that was the last view we had of the James Webb Space Telescope leaving the last rocket section. And so it got launched on Christmas. I celebrated by drinking champagne with my parents at 6 in the morning. They were indeed forced to drink champagne at 6 in the morning on Christmas. They didn't complain, which is much to their credit. So then this thing gets launched. It has to not explode on launch. And then as it is flying through space at thousands of miles an hour, it has to deploy first this sun shield, this tennis court-sized sun shield, which involves 300 individual deployments with single point failures. So if any of these gets mucked up, we are hosed. But everything went well. Then they have to align. They had to align this 21-foot mirror to less than to a precision less than the width of a human hair. And they had to do this all while hurtling through space. You know, as you recall, with the Hubble Space Telescope, the optics were not initially good, and we could send an astronaut up there to fix it. That was not the case with James Webb. If this mirror was not aligned by this first set of movements, and then what we could do from the ground, we were toast. Fortunately, all of these things happened perfectly, better even than we had anticipated, and the images from James Webb have been truly staggering. But I want to just pause, and I think it's worth asking, why would we spend billions of dollars, decades of time, to send this incredibly fragile, incredibly expensive telescope 1 million miles away where we can't fix it? What is this telescope going to allow us to do? And at a most fundamental level, this telescope is going to allow us to understand our cosmic origin story. It's going to let us understand where we came from, how the universe came to be, how galaxies came to have the properties that they have, look how they do, how stars and planets formed. So we're really launching this to try to understand how we got here. And the history of this is actually very interesting. So I wanted to just very briefly back up to the beginning. I know I don't really like history, and neither do you, but it's gonna be like 2 minutes. Just give me 2 minutes. So this image, does anyone know what this is?
That's the discovery of the first Cepheid in M31.
Yes. This is the Andromeda Galaxy. It doesn't look nearly as nice as it did on your Apple computer screen, but these little ends pointed to what Edwin Hubble thought were novae. And then notice that one of them is crossed out and says VAR because he subsequently realized that that was a variable star. And that is what allowed him to measure the distance to Andromeda and realize that this was not just a spiral nebulae in our own galaxy. This was in fact a completely separate galaxy, very, very far away by those standards. So with this discovery, this first image of Andromeda where we could measure its distance, this showed us that our universe wasn't just the galaxy. Our universe extended far beyond our galaxy to include other galaxies. And we've subsequently realized that there's trillions of galaxies in our observable universe. So with this new ability to look deeper into space, our understanding of our place in the universe shifted dramatically. So with the Hubble Space Telescope launched in 1990, we were intending to use this telescope to study nearby galaxies in somewhat greater detail. We weren't really intending to see really super distant galaxies. So the director at the time awarded time to a program with the Hubble Space Telescope, this director's discretionary time program, that selected to observe a single patch of empty sky, this patch, for about 20 days. People were enraged, obviously, because this was a catastrophic waste of time on an incredibly valuable facility. However, once they spent all this time studying this patch of sky, this is the Hubble Deep Field. And in this empty patch of sky, there were actually thousands of galaxies. And there's a couple particularly interesting features of the galaxies in this image. One, we thought that if we're going to see old galaxies, those galaxies would be relatively nearby because they would have needed time to form. And we didn't think galaxy formation could start right away in the universe because it would need time to build up structure. But when we looked at this image, we saw that there was these really old galaxies at really great cosmic distances, and hence early cosmic times, which means galaxy formation had to start much earlier than we had anticipated. The other thing that a postdoc who will remain unnamed at the time saw when she looked at this image was some of these galaxies, you can see, don't look anything like local galaxies. In her words, pardon my French, they're a fucking mess. So what that shows us is that galaxies had to evolve dramatically from early cosmic times to today. And with that lovely quote, they're a effing mess, the field of galaxy evolution was born. So this quote started my entire field. It is no wonder that I am profane. And it also happens to be the way that James Webb was conceived. Because all of a sudden we realized that we needed to be able to look back to much earlier cosmic epochs in order to answer our fundamental questions about the growth of galaxies in the universe. We needed to be able to look back to close to the Big Bang. So we want to understand how galaxies are forming, how they're growing, how they're building, how they're forming stars, how they're developing these weird, messy structures, and then also their regular structures that we see in the local universe, these smooth elliptical galaxies and these rotating spiral galaxies. So galaxies are really the largest fundamental building block of the universe. The visible universe contains trillions of them. The galaxies are the home of basically all stars, planets, black holes in the universe. And despite our initial ideas to the contrary, they're not island universes. They interact with their surroundings. They're cosmic recycling plants. They accrete gas, form stars, and blow it back out into their surroundings, enriching their surroundings with heavy metals. So their formation is monstrously complex. As Lars has told me before, correct me if I get this wrong, if you actually wanted to simulate the universe with the requisite spatial resolution, it would require all the energy from the sun. Is that what you calculated? Yes, he is nodding. That is correct. Which highlights the synergy of observations and simulations, and also why we need new observations to drive our understanding of the universe. We simply cannot model the entire universe from first principles at the spatial resolution that we would need. So just to make sure we're all on the same page, a galaxy is a gravitationally bound object that contains gas and dust and gas and a lot of dark matter in most cases. So this is a much better picture of our nearest neighbor, Andromeda, and you will see that it has these kind of key features of galaxies. A bulge in the center where stars are kind of whirring around like bees in a beehive, and a disk. And Andromeda, similar to the Milky Way, is a fairly typical galaxy in the sense that if you were a random star and you were born in a galaxy, it would be most likely to be a galaxy like the Milky Way or Andromeda, a bulge disk system with about the same mass. So we're trying to understand how these kind of objects formed, how galaxies formed. And the problem is that most of the growth happened in the past. And so we can't just watch galaxies grow now and understand how that process happened. So there's two plausible solutions here. One is that we can do galactic archaeology. We can trace the chemical compositions and orbits and positions of stars, in particular in the Milky Way galaxy, and try to piece together the formation of the galaxy. So there's been a lot of progress recently by a lot of people here using Gaia. The other option is that you can do look-back studies, where you actually look back into the past. And the reason that this is possible is because we can use telescopes as time machines. We can use telescopes to look to really great distances. And because light takes time to travel, the light that is emitted will take some quantity of time to arrive at us, which means that we're seeing that object as it was in the past. For our nearest neighbor Andromeda, that's about 2 million years. So we're seeing, the light from Andromeda that we're seeing is about 2 million years old. So we can essentially use telescopes as time machines. And this was a concept that I found so mind-blowing as a second grader in Lee Hansen's class that I decided that this is what I had to do with my career. So I've been obsessed with the Hubble Space Telescope for a very long time. And I wish I would have worn the sweatpants to present today, though. That would have been a cool look. But with the James Webb Space Telescope, we're getting an even more powerful way of looking into the past. We can use these telescopes as time machines because the light takes time for us to travel. But the other key feature is that as light is traveling through an expanding universe, the wavelength increases. So light that was emitted in optical that we could see at early cosmic times is shifted to the infrared by the time that it reaches us. And so the Spitzer Space Telescope could look in the infrared to potentially see the light from these distant galaxies. But as you will see, we can't really resolve what's happening, and we can't really detect really distant galaxies. So this is, I don't know if anyone will recognize this image yet, or if it'll take actually transitioning to the James Webb image. So that is going from the Spitzer image to the first James Webb image released of the SMACS galaxy cluster. And as you can see, the James Webb image is just remarkably better. You can see not only the structure of galaxies popping out when you look at this, but you can also see all of these objects popping out of the noise. And those are the distant galaxies that we want to observe and we want to understand in order to understand the origins of our universe. So, now that we've gone through a very extensive introduction, I want to talk to you about some new discoveries with James Webb. First, talking about these galaxies that are too massive, too early. Then describing this new method I developed using slitless grism spectroscopy with the Hubble Space Telescope that we are now using with the James Webb Space Telescope to really enable us to probe the early universe in much greater detail, much more efficiently. And then finally talking about what the future looks like in terms of our resolved understanding of our universe. So when I first started looking at these spectacular James Webb images, the first thing I was looking for was objects that were detected in James Webb and not in Hubble or Spitzer, because, you know, to me, those are the most interesting objects because we couldn't see them previously. So I found this guy, and as I will describe to you in a second why we thought this was interesting, we found this object to be remarkably interesting when we actually determined its physical properties of it. My colleague Rachel sent this to my other colleague Ivo at night, US time, and by the morning he had found, he was in Europe, he found 6 more of these guys. And the reason these things are interesting is you can see in this plot. So this is a spectral energy distribution. This is how much light there is as a function of wavelength. So it's not a spectrum. It's like a poor man's spectrum. So you in this green is the average spectrum of previous galaxies that had been detected at the epoch that we're detecting these galaxies at. And the red is the galaxies we're detecting. So as you can see, the shape of the SED is qualitatively different than previous objects that we had seen. It's very, very red. And so these objects that we're able to select with James Webb are completely different than what we could select with Hubble previously. And when we fit them, we find that they have redshifts between a redshift of 7 and 9, which is within a couple 100 million years of the Big Bang, and stellar masses in stars of greater than 10 to the 10. So what we're seeing is, if this is correct, is that there are galaxies with the mass of the current day Milky Way 500 million years after the Big Bang. This is not something we thought was possible. We thought that the universe takes time to form galaxies. It starts forming little galaxies, and then those little galaxies gradually build up to become bigger galaxies. We did not expect to see Milky Way mass galaxies 500 million years after the Big Bang. So this was a really big surprise. We can put this in context by looking at how much of the mass density, the total mass density of the universe is in galaxies of a certain mass. So what this shows is that you're looking at these cumulative stellar mass functions at redshift 8 and redshift 9, and there's not very much mass in these high mass systems, and there's a lot more mass in lower mass systems. So if the fiducial stellar masses that we measured for these objects are correct, they're up here. So they are over an order of magnitude higher than expected from Hubble and Spitzer. So if this is in fact true, it could be the case that most of the stellar mass density of the universe at this epoch is contained in really massive galaxies. So if that's true, that completely changes the way that we understand galaxies to have grown in the early universe. There could be this fast track for really massive galaxies to form instead of needing to form hierarchically from lower mass galaxies. So a more fundamental problem, perhaps, is that our cosmological model, lambda CDM, makes predictions for the contents that should exist in our universe. And it does this by making predictions for the number of dark matter halos that have a certain mass, and then there's a certain ratio of dark matter to normal matter in the universe, and then that sets an upper limit, we think, on the mass that can exist in stars, in galaxies. Playing that forward, we think that in general, the universe can convert baryonic matter into stars at a rate of about 1%. Even if all of the baryonic mass was converted into stars at 100%, there's still not enough baryons to form these galaxies. So this is really pushing, if this is correct, this is really pushing up against what we expected for how galaxies could form in the early universe based on a lambda CDM cosmology. As a result of that, the internet got pretty excited. So I did a bunch of different interviews on a bunch of different things. One I was told yesterday, which was on a major news network. I've been told I am embargoed from saying which news network until it is released in a couple weeks. But I think one of the things that's really exciting about this is that, the taxpayers invest a lot in us to do science and to understand our universe. And so it's really exciting that JWST has actually kind of captured the imagination of the public media, and so that we can kind of communicate what we're doing more broadly to the people who are funding it, which is great. This Reddit post, I was told by the CU, the Colorado media people, broke the CU website actually, because they got so many hits based on the Reddit story, which was fun. So what's next here is we need spectroscopy. We need spectroscopy to actually validate that these objects are what we think they are. We need to be able to confirm their redshifts using spectroscopy, and we need to also understand how much of the red light is being contributed, for instance, by emission lines, which could change our interpretation of these objects. There have been some updates on this, which I'd be happy to talk about at the end if people are interested. So the punchline here is that galaxy formation began earlier than we thought. Things are happening in the early universe more quickly than we had anticipated. We can see this in other ways too, actually. So basically, if there are these really massive galaxies at very early cosmic times, what that means is that there need to be galaxies that are forming stars really fast and hence are really bright at even earlier cosmic epochs. So, if we're seeing these things at redshift 7 to 9, we probably need to see luminous galaxies at redshifts, 11 to 20 to explain the existence of these objects. And so this object, GNZ11, was discovered by Pascal Usch a couple years ago, and people did not believe that this was actually a redshift 11 galaxy because it was so bright. It was even detected in NICMOS imaging, which is, the predecessor to WIF 3, WIF 2. I think it was just NICMOS before that. But this thing's really bright. And so it basically is 10 to 15 times, it was found in an area, anyway, number density, whatever. This thing shouldn't exist. None of the models predict that an object this bright could have been found in an area as small as the area that it was found in. And so it really challenged some of these models to explain it. And so the thing that was needed here was spectroscopic confirmation. There's also been a number, dozens of additional very high redshift, very luminous galaxies that have been claimed with James Webb. And the thing that is needed with all of those is spectroscopy. So we got a spectrum of GNZ11 very recently, and it is spectacular. That might not look spectacular to you. That looks spectacular to me. That is redshift 11 object. It is, in fact, a galaxy. It is, in fact, at redshift 11, and it is, in fact, extremely luminous. The question remains, to a certain extent, how much its flux is being boosted by a supermassive black hole. But we do now have spectroscopic confirmation that this is real. And so it'll be really exciting over the next, hopefully, year to a couple years to see if all of these really high redshift galaxies are actually able to be spectroscopically confirmed. So in summary, we are seeing that the galaxies in the early universe are older and more massive than our models had predicted, than we thought that they had any right to be. And so that suggests that the way galaxies are forming in the universe is different than we had thought. And we're going to have to revise our understanding of how this happened over the next few years. And this This was actually a quote in the Atlantic. This was not our fault. The actual writer wrote this. So, you know, apparently she had originally put in chonky, but then her editors said, like, you can't write chonky in an Atlantic article, so they changed it to chunky. But point is, the chunks forever. Okay, so we've talked about the universe before JWST. We've talked about this discovery of these galaxies that are so massive that they shouldn't exist by our current understanding of how galaxies form in the early universe. The next thing I want to talk about is this slitless spectroscopic revolution, how we are starting to be able to use these much more efficient modes of spectroscopy to get a really extensive picture of the chemical, dynamical evolution of early galaxies. So, we're trying to understand how galaxies grew, how they assembled. And in order to do that, we want to map how they formed their stars. We want to watch how they're actually assembling. And so this, of course, looks familiar from the night sky. This is Orion. And if you zoom in on Orion's sword, I said that really awkwardly. Orion's sword, you will see the Orion Nebula. And this kind of reddish light in the Orion Nebula is H-alpha emission, is Balmer alpha emission. So this is a tracer of ionized gas, which is a tracer of very hot young stars. And, you know, of course, hot massive stars have shorter lifetimes. And so if they're there, ionizing their surroundings, that means you've had recent star formation. So this Balmer alpha emission is a tracer of star formation because, you know, it's essentially instantaneous on galaxy formation scales, which is 5 million years. So we've long been able to trace H-alpha emission in nearby galaxies. You know, you can see this magenta color that is tracing the star formation, the H-alpha emission in Andromeda. And so you can see where it is building. You can see it in the disk of this galaxy. So we've long been able to make these beautiful maps of H-alpha emission in nearby galaxies. But at earlier cosmic times, that was not the case. This is a not beautiful, not resolved image of H-alpha in a galaxy at about redshift 1. And so there was significant development in this field when we put integral field units with adaptive optics onto 10-meter class telescopes. That allowed us to, for the first time, map this H-alpha emission star formation in these galaxies at the peak of the cosmic star formation in the universe, the peak epochs of galaxy growth. The problem here is that the maps are beautiful, but the problem is it takes about a full night to do this for one galaxy. And if you've ever put in a proposal for VLT time, you know, the only way you're going to get a sizable sample is if you actually built the instrument. There is no other way you're going to get a reasonable sample. And even then, you're not really going to get a reasonable sample. So up until, you know, I think at this point, there are about 60 galaxies with this full spatial resolution information about how they're growing, which is what we want. We want to understand how they're growing. But then they put Wide Field Camera 3 on the Hubble Space Telescope. And on Wide Field Camera 3, there is this filter called a GRISM, a grating prism. And with this grating prism, we can do this new kind of spectroscopy because, in particular, with Wide Field Camera 3, this GRISM had very high spatial resolution and very low spectral resolution. And so that allowed us to get spatially resolved emission line maps for galaxies near the peak of the cosmic star formation history. So these are some examples. So I developed this method as part of my PhD thesis. And basically it allowed us to, these might not look beautiful to you, but compared to what there existed before, just take it on faith. These are spectacular. So with this new method, we went from being able to map the growth in about 60 galaxies, map the star formation in about 60 galaxies, to about 3,200 galaxies. So that's a significant gain in our ability to do statistical studies of how galaxies are growing at the peak of the cosmic star formation history. So this was used by people to study a range of different things, like how star formation drives galactic winds, ram pressure stripping of gas and galaxy clusters, and this PhD thesis that I helped advise on how the properties of star formation change as a function of environment. I also use this for a number of different, to answer a number of different key questions about how galaxies form and grow. Namely, how galaxies form their stars and quench their star formation, how they grow in size, and how they build their structure. And I will not have time to go into any of those, besides to very briefly show some work I did with Lars on how galaxies quench their star formation, which is a synergistic project between this new observational method and his cosmological hydrodynamical simulations. So basically what this allows us to do is we can actually map how star formation is shutting off in galaxies. How star formation shuts off in galaxies is one of the key open questions in the field of extragalactic astrophysics. There's a lot of gas, and that gas should be able to turn into stars, and it's not. And these galaxies are dead. And so we're trying to come up with ways that we can probe how this process happens using the data that we have. And so this gave us some exciting this new method gave us some exciting new insights into how this happens. In particular, we can see that if you look at the star formation rate divided by the stellar mass, so the specific star formation rate is how much is basically the relative amount a certain patch of the galaxy is growing. You can see that it is centrally suppressed. So galaxies are basically quenching from the inside out. And that's neat. That's a nice observational descriptor. But when you combine this with the power of a cosmological simulation, like these ones of Lars, you can actually develop some understanding of why this might happen. So the simulation is a nearly perfect match to the observations. That's this orange and the black. I guess it's more salmon colored. And we looked at what might be driving this in the simulation, and we find that this agreement is actually driven by AGN kinetic winds, supermassive black hole kinetic winds driving gas out of the center of these galaxies. You know, it could be something else. The referee had other opinions, but at least in this simulation, the reason that how galaxies are shutting off their star formation is that they are driving gas out of the centers of them with a supermassive black hole. So that was how we used this new method for doing spectroscopy with the Hubble Space Telescope. That's how I pioneered this method. It happens that James Webb is also equipped with a number of these grisms. And so using the same method that I developed for my thesis, we can start to understand how galaxies are growing at much, much earlier cosmic epochs with James Webb. This is data from the FRESCO program. So FRESCO is a GRISM spectroscopy program led by Pascal Huche. And you can see this is a normal direct image. You can see all the happy little galaxies in here. And then this is the GRISM image of that same field. So you can see this resolved galaxy structure in that emission line of that galaxy. So there is thousands of spectra from this program, and we just got the data, so we're just starting to dig into it. But it really provides emission line diagnostics, which, as I said, are a tracer of star formation, but they're also a tracer of the chemical composition of galaxies. And in the case of FRESCO, as I'll talk about in a second, they also give us information about the kinematics of galaxies, which is how galaxies are rotating or how they're supported dynamically. But this figure just gives you kind of a sense for the broad range of science that we can do with a program like this, because we get these different emission lines at all these different redshifts. So, we at very low redshift, we're actually getting 3.3 micron PAH emission. We're getting bracket alpha. And then for a ton of galaxies, actually, we're getting Passion alpha. So Passion alpha allows us to study the kind of stuff that I was just showing you, except without the concerns of dust attenuation. So we can look at how galaxies are growing at a redshift, redshifts around 1 to 2, without worrying about dust attenuation. So that's a very powerful probe. You can see we get H alpha at around a redshift of 5.5, and then we get O3 and H beta out to almost a redshift of 8. And so this is really allowing us to do exciting science across a huge range of cosmic history. One of the things that I'm most excited about, hopefully I'll get this out like this week or next week, but one of the things we found is that, so this is a direct image of this galaxy at redshift 5.3, so that's the first billion years of cosmic history. And this is its direct image. This is its GRISM spectrum, or just the emission line in its GRISM spectrum. And what's going on there? It's rotating. This thing is rotating, and and I flipped the axes. Sorry. This thing is rotating fast. This is like 2 orders of magnitude larger rotation velocities than have ever been seen at this epoch. So this is a massive galaxy, and again, similar to the mass of the Milky Way, and it is rotating very rapidly and has fairly low velocity dispersion. And so this is really surprising. In these early cosmic epochs, galaxies are being constantly bombarded by other galaxies merging into them. And so the ability to form a stable disk is very surprising. And the ability to form a very massive stable disk at these early times is very surprising.
Question about that little right plot. Are those axes reversed?
Yes. No, it's actually this one. This one is reversed, yeah. Sorry. Yeah. Yes, you're right.
Okay, thanks.
Sorry.
It makes perfect sense.
Clear as mud. Yeah, sorry about that. This is, as you can tell, a work in progress. Okay, so finally, and I think I have, like 3 minutes? Something like that?
Have another 10 or so.
Oh, sweet. Okay, great. We don't have to rush as much as I thought I would. Okay, so we're talking. So slitless spectroscopy, GRISM spectroscopy is a really exciting avenue in order to understand more detailed information about the early universe in a way that doesn't involve the pre-selection of objects, so we're not biased. So there's a lot of room for serendipitous discoveries in this mode of spectroscopy, which is very exciting. Another object, or actually we found a number of objects that appear to have falling rotation curves in their kinematics. So I'm also working on getting that written up. But you know, flat rotation curves are the hallmark of the dark matter model. So we're seeing a lot of galaxies at around a redshift of 1 to 2 that seem to have falling rotation curves, which is interesting. Okay, so we talked about slitless spectroscopy. Finally, I want to talk about our resolved understanding of galaxy growth, and this is where we'll finish. So up until this point, we have generally, people in general, this seems surprising given like this image, but we generally treat galaxies as point sources. We don't actually, we just put apertures around them and we sum up the light and then we model that light, and that's what tells us about the physical properties of the galaxies. But as you can see, there's a lot of structure in these galaxies. And so if you're assuming that they're one single uniform blob, you're missing a lot of information, and you're also getting a lot of information wrong. So I wanted to just talk about what the resolved information that we're getting from James Webb is telling us about the universe. So one of the things that we can do with this new James Webb data is we can look at these galaxies that were not previously detectable, like the ones I talked about at the beginning, with the Hubble Space Telescope. So we've long known that there were galaxies that were HST dark, Hubble dark. Like they were dark at optical wavelengths, but very bright at infrared wavelengths. So we detected them with Spitzer and with Herschel, but we couldn't actually resolve them. We don't know what they look like. So this is an example from the SMACS cluster. So this is the HST image and the JWST image. So, oops, go back. Yeah, so see that big fat red guy? Yeah, so that is an HST dark galaxy. And it turns out that, you know, so we've known about these for a long time, but we couldn't resolve their rest optical light. And with James Webb, we can, and there's a number of surprises that we see. So these are, in general, these are redshift, slightly low redshift, redshift 2 to 6, massive dusty star-forming galaxies. And generally, when we think of these, oh, here's another example. Look at that bad boy. In general, when we think of these HST dark galaxies, we think of these, you know, big train wreck mergers, very dusty, you know, compact objects. Instead, some of these things we're seeing are these red disky-like objects. These are UFOs. If, you know, I know people are asking you if we've found aliens with James Webb yet. I get asked this on almost a daily basis. So now you can see the answer is yes. You heard it in colloquium today. We have found UFOs in James Webb. I'm kidding. It's the UFO stands for Ultra Red Flattened Object. It is a contrived acronym. I'm not sorry. I'm a little sorry. So these objects, these ultra red flattened objects, are basically HST dark galaxies, which we are able to resolve for the first time thanks to James Webb and its ability to, and its high spatial resolution at infrared wavelengths. So there's a couple surprises about these. First is that they have, we expect things that are very dusty to be compact. I wrote about this in this 2014 paper Lars referenced. We expect these to be very centrally compact objects because we need to have high dust column density towards their centers in order for them to be that obscured. And in fact, what we're seeing, and this is a paper in preparation by my graduate student Justice Gibson, these things are nearly exponential. They're basically, they have disk-like surface brightness profiles. The other thing we expected to see is high projected axis ratios. So bear with me. So if something is a spheroid, then we expect to see that at any direction that is oriented with respect to us, we expect it to have a similar ratio between the b-axis and the a-axis, right? So you're always going to have something with a with a high axis ratio, basically. So we're expecting to see these kind of spheroids, right? These compact spheroids with high dust attenuation. Instead, what we're seeing is that they have very low projected axis ratios. So if something is a disk, then we should see it basically have a flat distribution in projected axis ratio, because we could see it edge on, face on, and anything in between. The fact that we're seeing these things with only low projected axis ratios is actually quite strange. The thing it is most consistent with is a prolate distribution. We do not actually think that these things are prolate. That would be very surprising given that they're massive, and the only things that are prolate are usually low mass. But we think we're preferentially selecting edge-on disks is what we think is happening. These things are also surprisingly red throughout their disks. We don't see strong color gradients. And this is surprising because of a bunch of other work that has been done already with James Webb, in particular by Tim Miller, who is a finishing PhD student, and Ren Cease, who is a postdoc. And basically in most galaxies, we see that their centers are much redder than their outskirts. And so the fact that these objects do not have blue outskirts is quite surprising. So most galaxies do have these color gradients. And most galaxies look very different in different wavelengths. As you can see, I have this weird note here. Didn't mean to do that. My graduate student, Chloe Benton, is currently preparing a paper on the prevalence of bulges in galaxies, in James Webb relative to Hubble. We're seeing a lot more prevalent bulges. So this spatially resolved information is really telling us, is able to tell us how galaxies are growing, right? Things look very different at redder wavelengths than bluer wavelengths. That tells us about the resolved dust content, the resolved star formation histories, how galaxies grew. It also gives us, I'm just going to skip this, but in order to actually extract that information, we need new tools. In order to actually develop a physical understanding of how galaxies formed in a resolved way, we need new tools. And the reason is that up until this point, we've been treating galaxies as points, and so we've only been getting their physical properties on integrated scales. And the codes that we have to do even that are very, very slow. And we're essentially incapable of taking into account varying spatial resolution across objects. So it is with that in mind that we are developing this code Pirate. So Pirate is based on the Prospector code developed here by Ben Johnson. And so this is Prospector resolved, like Prospector. So we decided to call it Pirate. So that's where that came from. This code is called Pirate. It is in development. It's a hierarchical Bayesian inference framework to measure the spatially resolved physical properties of galaxies. And so basically it's this, you need to forward model all of the pixels and their stellar populations, accounting for the varying point spread function in each different image at each step. So this is very computationally intense, and the only reason that we're actually able to do this forward modeling is because of this neural net emulator that one of our graduate students, Elijah Matthews, developed, which gives us a 10,000 times speed up. Before that, it was simply impossible to do this project this way. That neural net emulator is called Parrot. Get it? And then we have a simplified testbed, which is called Pegleg. So my main, if we're being like fully honest, my main job here is
this man right here is my great grandfather. He's the first cat herder in our family. Herding cats. Don't let anybody tell you it's easy.
anybody can herd cattle. Holding together 10,000 half-wild short hairs, well, that's another thing altogether. Being a cat herder is probably about the toughest thing I think I've ever done.
I got this one this morning, right here, and if you look at his face, it's just ripped to shreds, you know?
You see the movies, you hear the stories,
So that's me. I'm the cat herder. I'm not the PI. I'm really the PCH, you know, principal cat herder. This code is in active development, and we're really hoping with this code to actually be able to answer a lot of the fundamental questions about how galaxies grow in the early universe. In particular, how they evolve in size, how they evolve in structure, how their star formation is quenched, how they build. And this tool is really particularly important for James Webb because the resolution changes by over an order of magnitude across the wavelength range of the telescope. And so we really need a tool that can accurately account for that. So in conclusion, galaxies are older, more massive, and diskier earlier than we thought possible before James Webb. And the early universe seems to be able to build these massive organized structures much, much more quickly than we had thought. Grism spectroscopy is going to be a powerful way with James Webb to get much more detailed information about how galaxies form in the early universe. And we're building tools next generation tools that are going to actually allow us to really understand the growth of early galaxies for the first time. This is a very exciting time in our understanding of the early universe. This telescope is going to be up for 20 years, and I think what we can do with it is only limited by our imagination. Thanks.
We have time for some questions if anybody has any that they want to ask Erica.
Yeah, presumably it's at the moment not a lot harder to tell if the mass function of galaxies at that redshift is heavily boosted towards this massive end. Is it only the massive galaxies that you're making that early, or are you also making small ones?
Those are all questions that we don't know the answer to yet. Yeah, we're basically still, this is the first 6 months of data. So, we're still not even really, I don't think there's really not been a complete mass function even that anyone's even come out with yet. So we're still waiting to see. Yeah, it's a really exciting time. We don't know yet. So we'll see. I think one of the big challenges is that our modeling tools are based on the local universe, and so a lot of the ways we translate light into mass are particularly challenging at these early times. Yeah. Yeah.
Very nice talk. In your red flat galaxies, as you see that galaxy, really exclude there is no blue, could be an instrumental effect, a matter of sensitivity, surface brightness, whatever.
There is, so we selected them to basically not have much blue light. So they're basically selected to not be detected in Hubble. But even, when you're even looking at like the, slightly redder wavelengths, like K-band or something, they really don't seem to have color gradients. If anything, you're gonna, it's hard, that was a really surprising result to me. So we looked at this in a bunch of different ways. We measured the sizes and, in different wavelengths. We looked at, the amount of flux in different apertures, and it seems to hold. So I don't think it's an instrumental effect, but it is very strange. I mean, the guess at this point is that if they're just mostly edge-on disks, that you wouldn't see the normal color gradients you would if they were face-on. So that's my current physical interpretation, but I think we really need spectroscopy to kind of see if they're actually rotating or if they're prolate or something.
briefly mentioned that the rotation curves of distant galaxies are not as flat as you expect. Could you elaborate on that and what you might imply about the role of dark matter in galaxy formation?
Yeah, that's it's a very preliminary result. We just literally saw it in the data and we're like, what the? So the yeah, basically, you see these rotation curves which turn over, which suggests that the centers of galaxies are very baryon dominated, and you really require more extensive modeling to get a better sense of what is actually going on, but it does suggest that there's not very concentrated dark matter. Yeah.
It's very fascinating that the Milky Way mass galaxies are already formed in such high redshift early universe. I was wondering if these galaxies have distinct structure like Emergence as in the local galaxies.
Yeah, great question. So these Milky Way mass galaxies are really early cosmic times. They have about the mass of the Milky Way, but they're 30 times more compact. So they're very, very compact. So they're very, they're very dense and probably going to end up being the dense centers of massive elliptical galaxies or the centers of galaxy clusters. So they're very different structurally. They are slightly resolved for the most part, so they're not just point sources, but at this point, we probably need to find some in a lensing cluster to actually, like you were asking, to get a measurement of, their structure, their bulge disk structure. So hopefully we can find some in a lensing cluster, and then we'll actually be able to figure it out. Good question.
In the HST dark galaxies, is there any indication that there could be an AGN in any of them, or a central bright source of some description, or is there nothing there that you can see so far?
Yeah, we haven't seen any indication of an AGN so far. But that being said, I haven't really looked at their X-ray fluxes. If for an AGN emitting in ultraviolet and optical, it would likely be very obscured by that disk, because all that light would have to go through the disk. So we haven't seen that. Yet, but it would be really interesting if those things do have active electric nuclei. Yeah.
Any questions online? No. Any more questions for Erica? So she'll be around a few more days this week if anybody would like to meet her, and she's also giving another talk tomorrow related to diversity, equity, and inclusion for those of you who are interested. So let's thank Erica again.